Okay, let's go ahead and start so we'll have time to get a good chunk of these notes out of the way today. Um, a looming deadline here is the due date for this very first homework assignment, right, on differentiating natural logs. So we've talked about that a little bit in class, right, already. So that one is actually due tonight at midnight. So you can continue to email me. I will through Ask Your Instructor, right? If you have questions, I'll try to respond if it's before about 9 o'clock. But after 9 o'clock, it's going to be iffy if I will respond. So if you have, if you're doing it right at midnight, you're kind of on your own. Or if you're finishing it right at midnight, but otherwise I'll try to respond. But if the questions are too complex for me to answer via email, then I won't be able to do that either, right? So but you can try. Okay, so that's due at midnight, right? And then we've got this other one, but this is not due yet, so because we're really just going to start talking about the notes. So this is about integration, which is really why we developed the natural log function anyway, right? Is to help us integrate. So this is really getting into more of the real meat of the course, other than differentiation, right? Which is really kind of the main topic of Calculus 1. All right, so finally we'll have a homework assignment in the grade book after midnight, and so we'll have something here, right, to look at under grades. Forgot what I was going to say. Yeah, I can't remember. Okay, it'll come back to me. All right, so that's where we are. Oh yeah, I know what I was going to say. Don't forget now, even if you're not completely finished at midnight and there's still things you think you can do on the homework, then you can run past the due date by asking for an automatic extension. So wait until after the due time though to ask for the extension, right? And then so you have a window there after the time that it's due to ask for an extension, and then you can continue working on it for a couple of days. You will lose points on the things that you do after the due date, but you can still earn additional points, right? So don't forget about that option. The instructions here are in somewhere in those announcements. Look down, and the instructions are there, or it's also in the syllabus on how to actually ask for that automatic extension. Okay, but again, wait until after it's due, because if you ask before it's due, then that extension request comes to me, and but it doesn't have to come to me. You can get it automatically if you follow the instructions for asking for an automatic extension. Let's see. Okay. So if I hadn't mentioned this before, when you're doing the homework, I do want to caution you on just a couple of things. One of them is there's lots of software available on the internet, okay? And if you're not familiar with it, you will quickly become familiar with it, because people will clue you in that this software exists. Like Symbol Lab is one of them, one of the websites, and there are others that you can that are very good at doing symbolic manipulation. I mean, they can do symbolic calculations, right? Not numerical calculations, but calculations with variables, right? So they're very good at integrating expressions or taking the derivative expressions, and those tools are great in their place, but you have to be very cautious about using them. So, you might want to use them to check answers, okay, for instance, right? After you have try to do by hand a question, but do not come to rely on these things exclusively for doing your homework, thinking, oh, I'm going to be able to use these tools to get a high homework average, and then that will just contribute to my final grade. Because, of course, what will happen is yes, you can get a high homework average, but the majority of your grade is going to be on tests, and then of course you will have shot yourself in the foot, right? Because you won't be able to do these things by hand on a test. It's the same with calculators, okay? So there are of course calculators that can do symbolic manipulations, and those things are useful at times, but you shouldn't rely on them to do your homework. You need to try to do these things by hand, right, with as little assistance as possible, okay? Now, numerical calculations are a different story, right? Numerical calculations, so if you're having to compute a log, right, okay, or doing other types of computations, that's a little bit less restrictive, right? Some things for calculation purposes you have to have a calculator, right? Okay, you're not going to be able to compute the log of 5,000 very easily, right, without a calculator. Okay, so that's absolutely required. I'm talking about something that does calculations with variables, does operations with variables, right? Okay, like integrating or differentiating, that type of software. You have to be very cautious in using. Now, sometimes we may use it actually in class, okay, for demonstration purposes, or sometimes to help us with really difficult problems, okay, that it's unreasonable to try to do by hand. But those are special situations, okay. So watch out for this. Another thing is. Although students tell me that they don't really find these all that helpful, are the videos that are embedded in the homework. Okay, so be cautious about using those as well, because sometimes the video will be not just an example problem, but will be an exact duplicate of the problem you're working on. Okay, so you can see how to solve the problem, right? The very problem you're doing in the video. Okay, and of course that is fine in its place again, right, as a support, but not you don't want to overly rely on that, okay? So just to boost your homework score, because then when it comes time to take a test, you won't be able to do the test, right? So you really got to try to do your own work on the homework, right? Okay, just you and your calculator for computational purposes, and then if I provide a software tool, right, in the homework like Desmos and for graphing purposes, then in graphing is really sort of a computational task, then that's different, all right? So I know when you're over-relying on the software and when you're using it for legitimate purposes, all right? So don't over-rely on it, because that's going to come at the expense of your test scores, which are really the major portion of your grade, okay? All right. Okay, so are there any other questions about the homework right now? We've answered a few. So I have gotten emails on that, especially that log problem where you're computing logs, and WebAssign is being very particular about the decimal places that it wants. Okay, so I've answered several emails about that. Other questions on this? First assignment, right? Okay, so the homework is really as I probably said already, right? The homework is one part of your grade that you really do have a lot of control over, because you can submit answers to questions multiple times, not indefinitely, but multiple times, and so it really is possible to with effort to boost your homework score up to where it's really quite good, right? Okay, so you want to take advantage of that. You want to have a homework average, but not by over-relying on, Symbol Lab, for instance, okay, or whatever other tool that you may be aware of, right, to help you with these problems. Okay, I'm going to trust that we don't have questions. Remember, the Academic Sports Center is open, though, in North 925, right? Okay, so you still have time to go there today if you want to additional help on doing your homeworks. Okay, I'll also be in my office after class, so you can find me as well there if you have questions. Okay, all right. Well, we're going to jump right into the notes then, because we were right in the middle of a problem last time, and I want to finish this problem. So we had done kind of half of the problem, but there's another part to it. that we want to do. That's really a review of things from Calculus 1. And so you have done these things that we're getting ready to do before, but I just want to remind you of how this process works. So last time we had this function, natural log of x squared plus 2x plus 3, right? And we were looking for the local maxima and minima. That's the turning points, the peak turning points and the valley turning points on the graph of that function, okay? And so we went through that process last time, and so that was a good review, right, of how you go through that process in Calculus 1. So that's a major type of problem from Calculus 1. You get to practice that a lot in Calculus 1. And we'll get to practice it some in this semester, not as in this class too, this semester, but we won't be focusing on this as much as we did in Calculus 1. But there's kind of a second half to this problem as well. That's covered in Calculus 1, right? So again, we're considering this function, right? And last time we found the location of the turning point on that function. I had a graph of that function, so here's the graph. And so we had already seen from the graph, right, that there was a turning point right here. The x-coordinate of that, that's a local minimum, a valley turning point, and the x-coordinate of that was -1. It turned out that the y-coordinate of that turning point, I think it turned out to be natural log of 2. Is that what it was, natural log of 2? If you have your notes there, okay, that's the y-coordinate of that turning point. And so we can see that on the graph right, but we found the exact coordinates of that point analytically, right, with paper and pencil using our knowledge of Calculus 1. Now, the second half of that problem, the second question that usually goes with this kind of problem in Calculus 1 is, after you found the turning points, is are there any inflection points on the graph? Okay, right? Okay, so now we want to review how to find inflection points, and so last time though we had to remind ourselves, right, what is an inflection point? Okay, anyway, on the graph, those are a little bit more subtle things to find on graphs than turning points. Okay, turning points are usually very obvious, right? You can see turning points very clearly, but inflection points are a little bit less clear, right? What inflection points are. So remember, an inflection point is where the concavity of the graph changes. Remember, concavity means the curvature of the graph. Okay, and there are only two types of concavity. Okay, one is concave down. That's a graph that's sort of bowed down like this, right? Okay, and then there's concave up. That's a graph that's bowed up. So that's the two major categories of curvature, concavity, that we deal with in Calculus 1. So if we look at this graph, we can see, in fact, that there are different at different locations on this graph, right? There's different curvature, correct? If you start examining the graph from left to right, that's usually what we do, right? We sort of scan the graph from left to right. If you look over here on the left, you can see, right, although it's not that emphatic, right, but you can see that that part of the curve is bent down, right, a little bit. It's not a straight line, right? So it's bent a little bit, and it's bent just a little bit down. That is concave down. Okay, so this part of the curve is concave down. And where the curve is sort of bent upwards, right, so if you think of taking a straight line and bending it upwards, right, with all your brute strength, right, take the straight line and bend it upwards, then that is concave up. So the middle part of this curve, right, is curved up. It's concave up. And then back over here on the right, it's curved down again, right, so it's switched back to concave down. Okay, and so see, there are some changes in the concavity, the curvature of this graph as we're going from left to right. That means that we have inflection points, because inflection points are where the concavity switches from either concave down to concave up or concave up to concave down. So inflection points are kind of analogous to turning points, right? With a turning point, a local minimum or a local maximum, right, that's where the direction of the function changes, right, from increasing to decreasing or decreasing to increasing. At an inflection point, though, that's where the curvature or the concavity of the curve changes, right, from concave down to concave up, or vice versa, from concave up to concave down. So let's see, if we look here, at first we're concave down, right, and then we're concave up. So where does it look like that inflection point is located? See, they're really kind of tricky to pick out sometimes, right? Okay, different people may come to different people may give different estimates here. What do y'all think that is switched? Maybe right there? Somewhere maybe right about there? Yeah, I think I'm sort of pointing at it right, okay? But some people may think it's closer here. Some people may think it's further over here, right? Okay, so it's a lot more subtle to estimate sometimes the location of inflection points than to estimate the location of turning points, okay? So maybe somewhere right about there, right, is the first inflection point where it switches from concave down to concave up. And then over here on the right, see, there's another inflection point, right, because it switches from concave up to concave down. Where is that? I don't know, maybe right there or something like that, okay, right? So, if I ask you to give me an estimate for, if I ask different people to give different, give their estimates for where's the inflection point, then I'm going to get lots of different answers to that, right? Lots of different estimates for that. It'd be hard for me to argue that one person is right and another person is wrong if I'm just estimating it from the graph, okay? So this is a case now where we really need analytical methods, right? Okay, we really need paper and pencil methods so that we can precisely determine where those inflection points are so that all of us can come to an agreement on exactly where the inflection points are located, okay? All right, so so that's our task, right, is to determine where the inflection points are, okay? All right, so so that's the question, right? In the second half of this problem, does the function have any inflection points? I think it does, okay, because I think I can see them, right? And where are they, okay? So where are those inflection points? And that brings up sort of a larger question, just in general, how do we locate possible inflection points? So how do we determine possibly where an inflection point can be located on the graph of a function, all right? So what tool allows us to determine their inflection points? So what concept in calculus tells us about concavity, okay, curvature, not direction. Direction, again, means increasing, decreasing, all right? What tells us about increasing, decreasing? What tool from calculus? Derivatives, right, yeah, derivatives tell us, right, okay, so it's the derivative that tells us about increasing, decreasing, right, okay, right, the first derivative is what helps us understand increasing, decreasing. So what helps us understand curvature, okay, which is a little bit different concept than increasing, decreasing? Second derivative, right, yeah, okay, so all of the answers to about inflection points come from the second derivative, right, okay, and actually you really go through exactly the same process, to locate the possible inflection points as you do to locate the possible turning points, right, okay, except instead of using the first derivative, you use the second derivative. Okay. So if you've learned that process for, as we reviewed it last time, right, if you've learned that process or you remember that process, right, for finding possible turning points and then confirming that they are in fact turning points, then you can really also find possible inflection points, and you can also confirm that they are, if they are or not really inflection points, without looking at a graph, just by using the second derivative. Okay. All right. So. So that's what we have to do here, right? Now we have to find the second derivative. And fortunately, we've already found the first derivative, right? Okay? Because to find the second derivative, you're going to have to find the first derivative first, correct? But we had already written down the first derivative. So here's the first derivative that we discovered last time. Okay? All right. So our next goal then is to find the second derivative. Now that's a fairly complicated expression, right? To find the second derivative for, right? Okay? So we have to recall there, how do we find the second derivative for a function like this? What's the rule there that's going to help us with finding the second derivative? The quotient rule, right, okay? So I'm hoping now that you at least recall the term quotient rule, right, from Calculus 1, because it would be better if you actually remember the quotient rule, right, from Calculus 1. But let me remind you here of the quotient rule. So let me write it down over here. Let me see if I remember it correctly. So if I get it wrong, y'all can help me fix this, right? So remember, the quotient rule we use for finding a derivative, right, of a quotient, okay, right, like this one. Now, simple quotients, you don't have to use the quotient rule. So if the numerator is a constant or the denominator is a constant, it's really not necessary to use the quotient rule to find the derivative, okay? You have to use the quotient rule when the numerator is an expression in x, right, and the denominator is also an expression in x, correct, which is exactly the situation that we have here, right? So in the numerator, we have this expression with x in it. In the denominator, we have this expression with x in it, right? So this is a good time here to use the quotient rule. So what does the quotient rule say? It's not nearly as easy as the product rule, remember? What does the quotient rule, though, tell us about the derivative of a quotient? So what do we do here? What? Yeah, that's right. You take this derivative, right? So it kind of starts off like the product rule, right? You take this derivative of the top and then what? Yeah, just multiply it by the bottom, correct? Okay, and then you're going to alternate, right? Just like you do in the product rule, you're going to alternate derivatives. But instead of adding these two terms together, what do? Yeah, you have to subtract. So there's something to remember there. So it's the derivative of the top times the bottom minus the top times the derivative of the bottom. And then all of this goes over what? That's right. You keep the denominator, but you square it, okay? So if you forgot the quotient rule, now's a good time there to recall it. So, because it does come up from time to time, in any calculus situation. That's going to show up occasionally. All right, so there it is. There's the rule, right, that we can use to find that derivative, okay? All right, so that's what I want you guys to do now is to apply the quotient rule and find the derivative of f prime. There's no reason for me to go through those steps here on the board because I think you've done this successfully lots of times. So I want you to apply the quotient rule to find that derivative and simplify a little bit, but don't try simplifying too much, okay? So simplify your result a little bit, but not too much. You can keep, for instance, the denominator squared. You don't have to multiply that out because that's going to give you a really big, ugly product, right? Okay. So try that for me and let's see what we get, okay? Because that's kind of the necessary first step, right? We're not going to get very far in finding these inflection points if we don't have that second derivative, right? Without the second derivative, we're just sort of completely lost, right? We'd have to really just totally rely on the graph, which we've already said, right, is not going to be efficient for this problem to find the inflection points by using the graph. Okay, so Taylor and I are going to watch you do that, right? Okay, and once several of y'all get pretty far along in this process, then we'll stop and we'll write down what you got. Okay. All right. So now try to work fairly quickly here. You can talk with as always, you can talk with your neighbors. We don't want to make a career out of this one, so because otherwise we won't get very far into the notes. So try to go as fast as you can. You don't need to. What are you doing there? Oh, you're multiplying that one out. Okay, that's fine. Yeah. Thought you were squaring. Is that it? Okay. I think that's it. I can't recall exactly, but that's pretty close. All right, yeah, so see if y'all can simplify that a little bit. You don't have to simplify it too much. Just try to, just try to do the numerator and try to combine like terms. Make sure you put parentheses around that. So do those products in the numerator and see if there's any like terms you can add together. Okay. That's pretty close. Wonder if that's exactly right there. I may try double checking your arithmetic. I don't know exactly what the answer is there. What there?
I think that's what I got.
That's what you got? That's pretty close, but I'm not sure. Let's see. Yeah, when you're multiplying these two, look, put parentheses for that product there. Oops, I'm sorry. Yeah, write it like this. Okay, but is that, let's see, is that the right product there? Where's the original statement? Here? So here you, what did you have here to start with? what's the derivative of, so it's the derivative of the top times this, right?
Mm-hmm.
But what's the derivative of 2x plus 2?
Should be 2, right? 2x, right?
Nope. Yeah, no, what's the derivative?
2,
Yeah.
right?
2.
Okay.
Yeah. Yeah, all right. But you wrote down here 2x.
Gotcha.
Yeah, so you already made that one too hard. Now, what about for, what are we subtracting off? It's you keep this, right? So you did that times the derivative of this. What's the derivative of this? That is 2x. That is 2x plus 2, right? Oh, I see. Okay, so you get this squared, right? Okay, so is that what you were multiplying out there? So you're going to be off a little bit on this one, correct? Because you didn't need the 2x. Okay, so see if you can go back and fix that one. Yeah, okay. I think that's it. That's pretty close, okay? That's what I recall, but I didn't write it down again, so I think that's right. Okay, yeah. Y'all are going through the steps pretty good, but sometimes you're a little bit sloppy in your differentiation.
Because this is supposed to be a whole parenthesis here.
Yeah, that's right. Yeah, you need parentheses around that. Right. Around the first thing, 2x plus 2.
Yeah.
Yeah.
'Cause-
No, that parenthesis
that's
you
fine.
do, right. Because you're multiplying, right? You need here, like this, right? Because you're multiplying those two things, right? Yeah, there you go. Okay. Now, you're going to keep a set right there when you multiply those together, and then that minus sign has to get distributed. So, very easy to make a sign mistake here. Okay. So you end up with minus 2x squared, well, actually minus 4x squared, right? So minus 4x squared, I think that's going to be minus 4x and then minus 4, right?
Okay.
Yeah, okay. So be careful with your signs. Yeah, be a little bit careful with your signs. You know, signs are always ugly things, right? So I think that's right. That's what I've seen so far. Did you get the same thing? Yeah, that's pretty good. You don't need, it's not going to hurt anything, but you don't need to have parentheses in the top, right? Whenever you have a fraction, you have to have parentheses in the bottom because of the square. But you don't need parentheses in the top because a fraction bar always implies parentheses around the numerator. That's just understood. So you don't really have to write those in. Did you get it there? Yeah, I think that's right. Nice. All right, y'all are doing really well. So that bodes well. You're off in that last coefficient there, though. I mean, that last constant. Yeah, I think that's what I saw, okay, from other people. Now, of course, we're not done with this. We're not done with this derivative, right? Once we compute it, the second derivative, I should say, because really that's just the start of our work, right? All right. So I think a good portion of the class got it. Some people were off a little bit in their arithmetic. So if you didn't quite get it, you can go back and repair what you got wrong. So what did that turn out to be? So the denominator is pretty easy, right? Because you're going to take the original denominator and just square it, right? And you can leave that squared. You don't have to expand that product. It's easier to leave it squared like this. But what does the top turn out to be once you calculate those derivatives and subtract and simplify? What do we end up with in the numerator there? What is it now? What? Minus 2x squared, right? And then what? Minus 4x and a plus 2? Okay, yeah, I think so. All right, did you missed that one? All right, see if you can fix that. Okay, all right. So is that what most people got there? Is that right, Taylor? Okay, so minus 2x squared minus 4x plus 2. All right, so that's just step one, right? Is finding the second derivative, because we can use that right to locate the possible inflection points. Now, possible inflection points do not really have a name. Possible turning points correspond to critical values, right? But possible inflection points unfortunately don't have a special term for them. They're just possible inflection points. But you find those, right, by taking the second derivative and setting it equal to 0, right? Okay, so it's exactly the same process as finding critical values right, or finding possible turning points. So we want to take this and set it to 0, and then we have to try to solve that equation, okay? So, well, we saw an equation very similar to this last time, correct? So how should we think of this? Well, here you have a fraction that equals 0, okay? And so the only way a fraction can equal 0 is if the top is 0. So you can forget about sort of forget about the denominator, right? At least in solving the equation, you can forget about that denominator. So the equation that you really need to solve is minus 2x squared minus 4x plus 2 is equal to 0, okay? All right. Now, the other, one source of possible inflection points is where the second derivative is 0. But remember, there's another possibility where the second derivative is undefined, okay? Where the second derivative is undefined. And the second derivative is going to be undefined where the denominator is equal to 0. So notice here we're setting the numerator to 0 to look for possible inflection points. But there are also possible inflection points where the denominator is 0. So you also do have to think about this equation, but for a different reason. It's not because this is going to give you solutions to this equation. It's because these values that make the denominator 0 are where the second derivative is not going to be defined, okay? But this equation has no solutions, all right? That equation has no solutions because x squared plus 2x plus 3 equals 0 does not have any solutions. We talked about that last time, all right? So, so you don't have to worry about where the second derivative is undefined in this example, all right? That's not a problem. But we do have to worry about where the second derivative is 0, and that's where this expression is 0. So we have to try to solve this equation. Now, maybe this doesn't have any solutions either, but I think it does because we already noticed that on the graph there was going to be inflection points, right? So I think this equation must have solutions. Let's see if we can find them. Normally, how would you find, I mean, not normally, but what would be sort of your default method of trying to find solutions to this equation? What would you try first, in other words? Factoring, right? Yeah, sure, this is a quadratic equation because the unknown is squared, right? So you would certainly try to factor. You can factor this a little bit. Notice you can factor out a minus 2, and that's a little bit helpful. If you factor out a minus 2, did I do that right? Yeah, when you factor out a minus 2, you get left with x squared plus 2x minus 1 equals 0. And that just means that x squared plus 2x minus 1 equals 0. Okay? By the way, why do I know that? Because here you have 2 times this quantity is equal to 0. But the only way a product equals 0 is if one of the factors is 0. But minus 2 is not 0, right? No way. So that means the x squared plus 2x minus 1 has to be 0. So I can forget about the minus 2. You can also think of dividing both sides by minus 2, right? 0 divided by minus 2 is still going to be 0. All right, so now we reduced it a little bit, right? But unfortunately, that's as far as factoring is going to get us because x squared plus 2x minus 1, darn it, doesn't factor. Too bad that's not x squared plus 2x plus 1 because that factors really easily, right? But x squared plus 2x minus 1 does not factor. So solving this equation by factoring, unfortunately, can't do it, okay? So what's plan B? Quadratic formula, right? So we have to try to use the quadratic formula, okay? So we're going to have messy inflection points here. Well, that's life, all right? So, all right, so let's try that, okay? Except I'm going to let y'all try that, okay? So, so what are our coefficients here? 1 and what? 2 and negative 1, right? Okay, so can you remember the quadratic formula? I hope so, but if you can't, here it is. All right, so there's the quadratic formula. So see if y'all can find the quadratic formula. I think there's going to be 2 solutions to this equation. Try to write down the solutions in exact form for me first, and then give me decimal estimates. So you may need your calculator here. All right. The decimal estimates are really going to be helpful to us. Okay. All right. In this problem. So write it down in exact form if you can find the solutions. And then, so by exact form, I mean not a decimal estimate, but then write it down the decimal estimates. Okay. So I think you'll need your calculator a little bit. I don't think it's too bad, but a little bit there. Okay. So don't spend too long on this. You've all practiced the quadratic formula a jillion times. So even if you mess up a little bit on this one, you'll be able to do it on your homework and on a test. Sometimes it's a little bit harder when I'm under pressure and I'm staring at you and threatening you, right? Okay. Did y'all get it? Now, I don't know what the answers are, so if y'all don't do it for me, then we're doomed here, okay? What is that? Is that a 2? Oh, I thought you wrote square root of 1. I was going to say, why? How did you come up with square root of 1? Is that it? Okay, that's good. All right, so you can simplify that a little bit more by hand, but it's not really crucial. So use your calculator now to give me, there's 2 possible values there, right? So use your calculator to give me a decimal estimate for those 2 values. Yeah, a couple of decimal places is plenty. So what'd y'all get there? Oh, okay. So that I wonder if that. Wow, I need to. Too bad I didn't leave that graph up there because we could look at the graph and see if we think those are in the right spot. Okay. Those sound plausible though to me, right? Okay. Are you just double checking your work? Yeah. Okay. Mhm. I think that's pretty close there. Did you get something? 0.4 and minus 2.4. I'd like to. Is that what we saw on the graph? I can't remember. Is that what we saw on the graph of that thing? Okay. All right. I was wondering if it wasn't flipped there. I was wondering if the negative was 0.41 and the positive was positive 2.4. I was just thinking about that picture, but I can't recall what that picture looked like, right? Okay.
You can't quite take it out of this one yet, right? See, that's what you did here. You took it out of both of them, but you still have to.
Right. Actually, you can. I'll show you how to simplify this, but you can already get your decimal estimates from here. Yeah. Yeah. That's right. Yeah. Just go ahead and put that in the calculator. You can simplify it by hand a little bit, but not entirely. Okay. Is that right? Is that what the picture looks like?
Oh, I didn't graph it.
Oh, okay. All right. I see. All right. So, okay. All right. Is that? Did they get the same thing? Oh, okay, yeah. So so we got several people agreeing. That's probably it, right? Okay. Oops, sorry. Did y'all get something?
The final one, isn't it? To put that in a calculator, or did I just
Yeah, yes, you did something wrong because you just forgot that. Remember, you have a plus minus here all the way down, right?
Yeah, so what does that mean, right? I had a plus minus right here too, or does that not?
Yeah, well, that means you cannot. I think you're trying to divide out these twos.
Oh, you can't do that?
You cannot divide out those twos.
Okay.
Well, not quite. Actually, you can, but it's not quite as easy as you're making it. All right, you have to do a little bit more work, right?
Okay.
Yeah, that's right. Yeah, okay. All right, so try that in your calculator then to get estimates for that, right? Okay. Oh, you didn't bring your calculator? Do you have a calculator on your phone? Do you have a phone? Oh, so all right. So there's almost, but that 2, you didn't quite simplify that, right, Janaya? Good try though. Square root of 8 doesn't quite simplify like you have it. Okay, all right. But I'm going to show you all that. All right. That's always hard. All right. Oh, yeah, okay. So you're almost there, right? All right. Let's see. Everyone almost got to the, if they didn't, to the decimal estimate. Okay. So let's see. When you substitute there A, B, and C right into the quadratic formula and do a little bit of arithmetic, I think you end up with, well, I don't know what you end up with. What do you end up with there? Is it minus 2? Does it start with minus 2? Plus or minus the square root of 8 over 2? Okay. So I think most people got to that point, and now really this is really good enough, because you can go ahead now and use your calculator to estimate square root of 8, right? That's not a perfect square, so you'll have to estimate that. But and then so estimate square root of 8 with your calculator, and then actually reduce this, and you can get decimal estimates for the x-coordinate of your two possible inflection points, right? So I think those turn out to be, I don't know, is it minus 0.241 and 0.41? So I think it comes out like that. Let's look at the graph. Let's look at the graph here and see if that's what we think that is. So minus 2.41. So about right there. Yeah, that looks like that could be an inflection point about right there, right? And then over at about 0.41, which is about right here, yep, that looks like that could certainly be the second inflection point, correct? Because it looks like indeed the curvature is changing about right there from concave up to concave down, and then over here at about minus 2.41, it looks like it's changing from concave down to concave up, right? So, I think that gives me a lot of confidence in those two decimal estimates. Now, look, you could, but it's really not necessary in this problem. You can simplify this a little bit by hand before you go to the decimal estimates, because let me show you here. The trick is you have to write 8 as a perfect square times another factor. That's what you want to try to do. So how can you write 8 as a perfect square times another number? Yeah, 4 times 2, obviously, right? So, and the reason you want to do that is you can extract the square root of 4, because 4 is a perfect square. So you get minus 2 plus or minus 2, because the square root of 4 is 2, and then you have this 2 left underneath square root. And now notice 2 divides into both of your terms in your numerator. The 2 in the bottom, you can divide it into both of the terms in the numerator. So you get minus 1 plus or minus square root of 2. There is the hand simplified version of the two possible the x coordinate of the two possible inflection points. One of them is minus 1 minus the square root of 2. That's this one. And the other one is minus 1 plus the square root of 2, which is this. Okay? So you can simplify that by hand, but you cannot completely simplify it by hand, because 8 is not a perfect square, right? So you're going to get left with a radical unless you get a decimal estimate. All right, now, so there are the possible inflection points, right? Okay, that's the x-coordinate of the possible inflection points. So how do we write down both coordinates of the possible inflection points? What do we do there? Yeah, that's right. You plug those x-coordinates back in where? The original function, right? Okay, so for instance, for this inflection point, right, you know the first coordinate is approximately, right? Okay, 0.41, and then take the 0.41 and plug it back into the original function, right? That give you an estimate for the y-coordinate, okay? So here's an estimate for one of our inflection points, and then the other one is at, well, minus 2.41, right, and f of minus 2.41. So clearly you'll need a calculator there, right, to get an estimate there for your second coordinate. So those are possible inflection points, right? Okay, we've already seen from the graph now that those really are inflection points, because we snuck a peek there at the graph. But if we weren't looking at the graph, how do we test those? So if you want to test to see if this really is an inflection point, what do you do? So how do you confirm on with pencil and paper that this really is an inflection point? It works just like how you confirm that a possible turning point really is a turning point, right? You have to make a very rough sketch of the graph, right, by hand. Very rough, right? Okay? So essentially, you have to look at the graph just like we did with Desmos, okay? But remember, you're doing this by hand. So let's see, somewhere over here on the x-axis is about 0.41, right? And we want to pick what? Numbers to the left and right of 0.41. Let's start to the left. So what's an easy number to the left of 0.41? 0. Yeah, sure, right. Try 0, okay? Because that's easy to do arithmetic with 0. And then what about over here? This is on the left. What about over here to the right of 0.41? Yeah, let's try 1. Okay. By the way, when you pick the number to the left of 0.41, of course, 0 is kind of the obvious choice, right? But don't go too far to the left of 0.41, because if you go too far, you're going to go past your second inflection point, right? Okay? You don't want to do that, all right? So make sure you don't pick this number like at -3 or something, right? Because that will be already past this inflection point. All right, now, what do you do with the 0 and the 1? Plug it into what? Not the original. Second derivative, right. Yeah, plug it into the second derivative, okay, and look at the sign, because the sign of the second derivative is going to tell you the concavity, right, of the curve. Whew, let's see if we can do that. Maybe it's not so bad, all right. So let's calculate there f double prime of 0. See if I can remember the formula for f double prime. What was it? Is this it? Yeah, there it is, right? Okay, so when we plug 0 into this, what's going to happen? Can we do that easily? What happens in the top when you plug 0 in? 2, right? Okay, and what happens in the bottom when you plug 0 in? Well, these two terms become 0, so you get 3 squared, which is what? 9, right? Okay, and what's the sign of 2 ninths? That is positive, right? Okay, so what does that tell us about the shape of the curve at 1? It's concave, is it what? Up, right, okay. So is that right? At 1, was it concave up? Oh, this is 0, okay. So at 0, right, it's concave up, all right. I was confused which point we were checking there, right? Yeah, so at 0, it's concave up. And is that what we saw on, is that what we saw when we made the graph? At 0, right there? Yeah, concave, this portion of the curve is, see, you're over here in this valley portion of the curve, right? That is concave up. All right. Now we have to check also 1. Of course, what are we hoping will happen at 1? What? So what are we hoping f double prime of 1 will turn out to be? What? I'm going to start, okay, so I can see I'm going to have to call people, so I shall start doing that. So what are we hoping is going to happen at 1? Yeah, we're hoping it's negative, right, and concave down, because that means we would have had a shift in the concavity, right? Okay, that means we would have had a shift in the concavity, and so that means we have an inflection point, right? Okay, let's see what does happen at f double prime of 1. Can I calculate that? All right, so when you plug 1 in here, what do we get? That's going to be what? That's going to be what? So when we plug 1 into the second derivative, right? Okay, there's the second derivative, right? So when we plug 1 in for x, right, that's what we're checking, that point. When we plug 1 in for x, what are we going to get for the second derivative? What's going to happen in the top? No, you don't need a calculator. Don't need a calculator. Just look at it term by term, because you're plugging 1 in, right? Okay, so you can do arithmetic with 1. You don't need a calculator for that. All right. So when you plug 1 in here, what do you get? Yeah. Here you get what? Here you get 2, right? Because you don't have any variable there, right? So you have -2, -4, plus 2, right? When you plug 1 in there, correct, right? -2, -4 is how much? -6, right? Okay. And then we have -6 plus 2 is what? -4, right? Yeah. So in the top you get -4. See, that's easy. And then let's see what's going to happen in the bottom. The bottom is also easy. Next guy there. So what happens in the bottom when we plug 1 in? Yeah, I don't know everybody's name, so I just have to say, hey, you. Sorry, okay? But, hey, you, okay? So what happens when we plug 1 in there, right? Sorry. What happens when we plug 1 in there into the denominator, right? So what's 1 squared? 1. 2, right? Oh, I'm sorry. We're doing the second derivative, okay? I went too far up there, but it's almost the same, right? Here's the second derivative, okay? So going to plug 1 in there, right? Okay, so when you plug 1 in right there, what do you get again? 1, 2, 3, you add those up is what? But we're squaring that, so 36, right, okay? So there we just get 36. So see, those calculations, right, you can carry out pretty easy in your head. Did we come out with what we wanted there, though? What's the sign here? I don't really care about the -4 over 36. What I really care about is the sign. And what's the sign? Negative, right, okay? Negative. So at 0.41, right? Right there at that point, the curve is switching from concave up, right? That concave up is bowed up a little bit, right? Concave down is bowed down. So if you're going to connect those two pieces, what's got to happen right here in the middle? At 0.41, what's going to happen? Next guy. Yeah, what flips? The concavity, right. Yeah, the concavity flips. This part is concave up, right? This part is concave down. So what's that point got to be there then? That's an inflection point, right? Yeah, because the concavity switches right there. Okay. The same thing. Now we're not going to test the second point, right? Okay. But I think that's going to switch from concave down to concave up at that second point, right? Okay. So this also is going to be an inflection point. So that's how you test, right, your possible inflection points to see if they really do turn out to be inflection points. It's possible to get these sort of phantom inflection points. They are these imposter inflection points. It appears that these points will be inflection points because they either make the second derivative 0 or they make the second derivative undefined. But when you actually test them, it turns out the concavity doesn't change there. Okay, so that situation does occur. All right. Okay. So there's how you find. There's a review of how you locate inflection points. Yeah. Oh, sure, right. Yeah, of course. You can just draw one for me. Okay, yeah. You can just draw a graph for me where you're going to have more than 2 inflection points, right? Because all you have to do is keep flipping what? Yeah, you just keep flipping the concavity, right? So if you have lots of hills and valleys, right, you're going to get lots of inflection points, right? Like this. See, that's switching from concave down, concave up, concave down, concave up, concave down, concave up, right? So that has lots of inflection points. Now, you might say, well, but what curve looks like that? I mean, that's kind of crazy. Dr. Wall, you just drew that, right? So no curve in real life, right, really looks like this, okay? But that's not the case, right? In fact, lots of curves look like this. What famous curve looks a lot like this? Sine curve, right, or a cosine curve, right? Yeah, it looks exactly like this. So sine and cosine example are example of functions with lots of inflection points on them. Okay. It's possible. Right, yeah, okay. Yeah, right, okay. All right. Okay, so, well, finally, that's the end of our first set of notes. So there is our lesson on natural log and differentiation of natural log, right? Okay. But again, as I mentioned, this is not really we didn't really develop the natural log function so that we can differentiate it. Although natural log function has lots of applications, and so we may be required to differentiate it a lot, okay? But that's not really why we created it. We really created it to help us with integration. So now we're going to switch back to using the natural log function for the purposes of integration, which is what we really were after, all right? Okay? All right, so so that's our next set of notes. We're going to, so we'll start that in a few minutes. Let's take a little bit of break here. We're kind of at a natural break point here. So let's take a few minutes to recharge our batteries here. So we'll come back at 5. Is that clock's right, finally? So we'll come back at 5 after 2, right? And start talking about how we integrate using the natural log function, okay? All right. Okay, so let's resume here with the really fun stuff. All right. So so we've been using this, right? This is just the differentiation rule for natural logs, right? So if you have natural log of an expression, and remember, actually, it can be the absolute value of the expression instead of just a simple expression, and you want to take the derivative of that, right? Then that's easy, right? It's just going to be the reciprocal of the expression, right? And then in the numerator, though, you'll have the derivative of the expression, okay? So that is just the basic rule, right, for finding derivatives of natural logs, okay? Now, if we think about that rule, right, and apply it to the problem of finding antiderivatives, what that means is we're really going to be sort of reading this equation from right to left instead of from left to right, okay? So if you read the equation from right to left instead of left to right, then you get this nice rule for finding antiderivatives. Antiderivatives, in other words, integrating, correct? Indefinite integrals of expressions like this one. So if you have an integrand, right, or an expression that you're trying to find an antiderivative of, and it happens to fit this format, so notice that's the reciprocal of an expression times its derivative, or you can think of it as this being in the numerator, so the derivative of an expression divided by the expression itself, all right, then the antiderivative of that is going to be just the natural log of the absolute value of the expression, okay? So that's going to turn out for us to be a really powerful antiderivative rule here, okay? Again, if you have an antiderivative that fits this format, right, where you have the derivative of an expression divided by the expression itself, then you're automatically going to know what the antiderivative is, okay, or what the integral is, right? It's going to be just the natural log of the absolute value of the expression. Of course, you have to add on your arbitrary constant there, right? Okay. Now, that looks like a very specialized rule at first, right? You may think, well, how many times am I going to encounter, integrals that look exactly like this? Okay. And the answer is, well, more frequently than you would think. Okay. And but even if we encounter an integral that doesn't quite fit this form, but is close to this form, derivative of an expression divided by the expression, then sometimes by using substitution, we will be able to rewrite the antiderivative in this format, okay? So it turns out that we can really make a lot of use of this particular antiderivative rule more than you would think, more than your intuition would tell you initially when you see the rule, okay? All right, so we're going to start going through here some examples of using this rule, okay? And I'll do some of them, and then I'm going to let you do some of them, okay? So you can get some practice with this before you get to your, this is the 5.2 homework. This is section 5.2 from the book. By the way, now, I've written this antiderivative rule out in words because I like to do that. But if you want to write that down symbolically in a little bit more efficient way, then here's kind of the way the book would write this out, okay? The book would say, oh, if you have a reciprocal of an expression, remember, you can be an expression in x, okay? So that can be some complicated expression in x. And then, but you also have multiplied in the derivative of this expression, okay? Or sometimes you write that in the numerator. So if you have du over u, all right, so the derivative of the expression divided by the expression, then the antiderivative is just going to be the natural log of the, don't forget the absolute value bars, okay, of the expression, okay. All right, so let's look at some very simple examples. This is about as easy as they come. So suppose we want to find the antiderivative of 2 over x dx, okay? All right, so here's how I would suggest, but, you know, it's not that this is the correct way of doing it, okay? This is my suggestion, but you may want to think about this in a slightly different way. Here's how I would think about going about this problem, okay? First, I'm going to look at the 2 there. That's a constant, right? And so I'm going to immediately think of, but maybe it's not a good thing to do, but I'm immediately going to think of factoring that constant out of the integral, okay? Remember, you can factor constants, not variables, but you can factor constants out of an integral sign, okay? That's okay, right? There's a theorem that permits that. So, so probably what I would think to do here is to take that 2 and put it outside of the integral sign, okay? And notice now that, and now here's where this requires a little bit of intuition, okay, or a little bit of, not intuition, but a little bit of recognition on your part, all right? So we factored the 2 out, and now we're left with this antiderivative, right? Okay, now here's where you have to, again, this requires a little bit of recognition. Here I have the reciprocal of an expression, right? So as soon as I see either a reciprocal or a quotient, right, a fraction in other words, that is where you might start thinking of, you know, can I use natural log? Now, that's not the only way to integrate a fraction. There are other ways as well, okay? But when you're, you know, when you're facing a fraction and you want to integrate it, one of the things that should be in your mind as a possibility is somehow this is going to involve the natural log. Maybe it doesn't, but it might, okay? Now, so does this fit into this pattern that will allow me to integrate it with natural log? Well, there you have in the denominator of this fraction, right, you have this expression x, and notice it's divided into, what's the derivative of x? 1, right? So see, here you have an expression divided into its derivative, okay? Derivative of an expression over the expression. That is exactly what you're looking for to integrate with natural log, okay? Notice, see, that's why, that's another reason why I took the 2 out, all right? So it was a good thing I had the foresight to factor out the 2, right? Because if the 2 were still here, this would not quite fit the pattern properly. You would have this expression in the denominator x, but its derivative is not 2, right? Okay, its derivative is 1. But when I factored the 2 out, then I've got exactly the situation I want for integrating with natural log. And in fact, the problem now is done, okay? Because according to this rule, right, what is the antiderivative of 1 over x going to be? It's just what? It's just ln of the absolute value of x, okay? So, see, it's just as fast as that. Once you realize that you've got, oh, an expression divided into its derivative, then that's it, okay? You're going to know what the antiderivative is. It's the natural log of the denominator, okay, of this expression. That's it, okay? Plus, don't forget the, you know, the necessary constant. WebAssign won't let you forget that for sure, right? Okay, so you have to add in the arbitrary constant there. So fast, right? Okay, very easy to integrate that expression. Notice we're not using the anti-power rule, right? Okay, we are not using the anti-power rule. Remember, the anti-power rule says you add 1 to the exponent, divide by the new exponent. Use that a lot for integration, but not here, okay? Using a different rule here for doing integration. All right, let's try another one then. Okay, so these are all in the same, right? See, these are all in the same section, right? So probably these are all going to involve natural log, correct? All right. So see, the minute you look at that integral, the first thing you should probably think of is, oh, this is a reciprocal of an expression, right? Reciprocal of an expression. So it's possible that I could use natural log. Maybe it won't end up that way, okay? But it's possible I could use natural log. Let's see here. So I have the expression 4x minus 1, right? And have the reciprocal of that. So it would be nice if I had here in the numerator what? What did you say? I'm sorry. Yeah, the derivative, right? What is the derivative of 4x minus 1? 4, right? Oh, darn, okay. I don't have 4 here, though, right? Okay, here I have 1. So I don't, unfortunately, quite have the rule met, all right? But I'm pretty close, right? Okay, I'm pretty darn close, okay? I'm not that far off. So I don't want to give up on quite yet on using natural log, all right? All right, so here's what I mentioned just briefly earlier, all right? The rule here does not quite exactly fit, but what I'm going to try to do now is use substitution. And let's see if we do some substitution, if we can make the integrand look like we want it to. Okay. All right. So we're going to switch here now to doing integration by substitution. Okay. But we will come back to natural log. All right. All right. So here's what I'm going to substitute for, and this is very common in these problems. I'm going to substitute for the denominator of the fraction. You'll see why this works out nicely in just a second here. So I'm going to pick my substitution variable, which is often u, right? Okay, doesn't have to be, but frequently it is. And so I'm going to let u be 4x minus 1, and then I'm going to substitute that for the 4x minus 1 in the antiderivative, okay? But now, but of course, we also have to get rid of the dx. So remember, when you're doing integration by substitution, you have to do a few extra steps here, right? First, you have to compute the derivative of u with respect to x, in other words, du dx, and then solve this equation for dx. What is the derivative of u with respect to x? So what's the derivative of 4x minus 1? Yeah, we just said that, right? It's going to be 4. Now, solve this equation for dx. So to do that, multiply both sides by dx. So I get du is equal to 4dx. And then divide by 4, right? I'm not trying to solve for du. I'm trying to solve for dx. So I get dx is equal to du over 4. So in my integrand where I have dx, I'm going to write instead du over 4, and that will completely get rid of the variable x, because remember, I'm also going to substitute u for 4x minus 1. So see, that's our goal. We're going to substitute here to get rid of x and kind of replace x by u. So let's see. What do we get here then? We get antiderivative of 1 over u, right? And then what was dx now? That's du over 4, correct? So there's my new integration problem. Now, is that better, really? Okay. The answer is yes. All right. Here's why. Here you're dividing by 4. That's a constant. So you can factor that out. Now remember, you're dividing by 4. You're not multiplying by 4. So you can factor out this 4 in front of the integral sign. But how does it factor out as? 1/4, right, okay? So it's not going to come out as just 4. It's going to come out as 1/4. So you get here 1/4 times the antiderivative of du over u. And see, that is perfect, right? Okay? Here you have an expression divided into its derivative. So you immediately know how to integrate this. See, so now we can integrate, right? Okay? So we can do the integration. What is the antiderivative going to be? It's ln, right, okay? So you keep the 1/4 because that's in front. ln of what? Well, don't go too fast on me. First, ln what? U, right. ln of the absolute value of u, okay? So that is first. And then you have to go back to x because the original problem was with x, not u. But what is u in terms of x? 4x minus 1. So you get 1/4 times the natural log of 4x minus 1 plus a constant. There it is. There's your answer. See, so we were able to pull that off after all. Even though we didn't quite have, just the derivative of an expression divided by an expression, okay? But after a little bit of substitution, we were able to get it into that form, okay? That's kind of going to be our goal in most of these examples, or maybe all of these examples in these notes, okay? All right, let's try another one now, except I'm going to let you do this one, okay? All right, so here will be your first chance to shine here. This looks a little bit worse, actually a lot worse, okay? Because it just looks worse, right? Okay, but you definitely have a quotient there, so we're integrating a quotient just like the prior two examples, and and you're thinking, well, obviously we're going to use natural log probably, right? Because this is a problem. This is the whole section is about natural log, so we're going to use natural log here. So what form do we want the integrand to be in? What form would we like this in? We'd like what? What's the basic rule there? Yeah, expression divided into what? Its derivative, right? So if you've got that, then you're in good shape, okay? So you can check to see if that's the case, all right? And if it is, then there you go, right? Okay? All right, so y'all try that one, see if y'all can. So if you've got it in the right form, you can write it down in 10 seconds, right? Okay, just as fast as your fingers can write there. Okay, it's easy. All right, so see what you get there, and then I'll show you the more complicated way of thinking about this. All right, so do we have this just like we like it there? Yeah, that's an integral, right? So you're just asking, do I have an expression divided into its derivative? So just look at that. What's the derivative of x cubed plus x? 3x what? Plus what? Is that this? Yay! So you've got it just like you want it, right? Okay, you've got an expression divided into its derivative. So you automatically know the antiderivative is going to be what? Natural log of what? Natural log of what? What was it? What was it here? See, here we had an expression divided into its derivative, and the antiderivative turned out to be natural log of what? X. So what's going to happen here? You're going to get natural log of what? No, not x. Okay? It's going to be the denominator. The denominator. Right? It's going to be natural log of the denominator. Yeah. That's the thing to remember. All right, so you got to ask yourself, are we in the right form? So what's the form that we want? No, I'm going to show you how to do it like that. But this one's a little bit simpler, just the way it's originally created. So all we're looking for is the same format, an expression divided into its derivative. If we have that, then we're in good shape. So here you have an expression, x cubed plus x. What is its derivative? 3x something.
Oh, 3x squared, 3x squared plus 1?
Yeah, 3x squared plus 1. Is that this?
That's this.
That's the derivative of this, but does that happen to be in the top there?
No.
It is, right? What did you tell me the derivative was?
3x squared plus m
which is this, right? Okay, so you have an expression divided into its derivative. Whenever you've got that, then it's easy to integrate using natural log. You just get natural log of the um, expression. Not the derivative, but the expression. So this is the answer here is going to be natural log of what? Not 3x squared, not the derivative, yeah, but the original expression. Yeah, that's it, in absolute value bars. No, everything. Yeah, there you go, all of that. That's it, yeah, okay. Plus a constant, all right? But that's only because we had this nice, simple format, right? Okay, expression divided into its derivative, right? Yeah, okay. Did you write it down there? Yeah, so easy, right? Okay. Yeah, see, just fast there, right? Yep, that's it, right? Okay. Y'all get it? Yeah. So it's just almost almost trivial, right? Okay. Looks terrible, but turns out to be really easy there. Oh yeah, there's the answer, right? Yeah. But don't add the constant there. What?
He
Mm-hmm.
asked how come
Oh yeah.
how come the one wasn't in front of it? And isn't it because one doesn't make a difference to the equation?
How come I don't understand your
So
question.
in the other example, you moved the numerator from over here, and you took it on to the
Yeah, I
side
did,
there.
right. Yeah, I did. So here you're wondering,
Can we do something similar, or why don't you move that numerator to the side of the, or over here? To the side?
because I didn't need to, right? Well, I couldn't have because this is two terms, but I didn't need to anyway.
Okay.
Remember, we want this into its derivative,
So you can
but
just
but this is the derivative, right? So there's no reason for me to try to change it, right? Okay.
If there's two terms, you don't move them.
You could not, yeah, two terms you cannot factor out anyway, right? Okay, yeah. So there's nothing I can factor there anyway. Did you write it down? Yeah, so see, so easy, right? Okay. Yeah, Janaya, did you just write down that, where is it there? Yeah, absolute value. Right, absolute value. Okay. Wow, see how fast that one was? So that looks like a terrible integration, right? When you first see it, it's like, wow, I don't know how to do that. But it turns out to be really simple, correct? Okay, just because of the format, we notice here. Okay, here I have this x cubed plus x in the denominator, but the derivative of x cubed plus x by luck turns out to be 3x squared plus 1, correct? Okay. And so I immediately recognize, oh yeah, I have an expression divided into its derivative. Whenever you have that situation, an expression divided into its derivative, it's going to integrate just super fast. It's just the natural log of the denominator, okay? So there we can see, oh, so easy. Antiderivative here is just going to be natural log of x cubed plus x, and then don't forget the constant. Now, the tricky part, though, is to recognize, and this is what's going to be hard, is to sometimes this format is difficult to see, right? So you may not immediately see, derivative of x cubed plus x is 3x squared plus 1. Granted, it's pretty hard to miss that, but sometimes you will overlook these things like this, okay? So suppose that you didn't just immediately see, oh, yeah, I have an expression divided into its derivative. Then, what could you do without quitting, all right? Well, let's try the substitution method, okay, that we tried on the previous problem. So another way of looking at this, and this is actually, in practice, this is what you're going to do 99% of the time, okay? You're going to look at this and say, you may not recognize immediately how to integrate it, but you'll say, wow, I have I have this fraction that I want to integrate, right? Okay, and I might be able to do that with using natural log. Might be able to do that using natural log, but of course, to use natural log, I've got to have it in just the right form. So to see if you can get it in just the right form, you can try substitution. So most of the time, this is what you're really going to do here, okay? You're going to use substitution to try to integrate this. So you will substitute for the denominator, okay? Going to substitute for the denominator, just like we did in this prior example. So we're going to write our denominator is x cubed plus x, right? And that's what I'm going to plug in for x cubed plus x in this integration. But now, of course, before you can do the substitution, right, you have to first compute what is the derivative of u with respect to x. So do not forget that step. What is the derivative of u with respect to x? That's 3x squared plus 1, right? Now solve this for dx. Solve this equation for dx. So multiply both sides by dx. So you get, so you're going to multiply dx on the left and dx on the right. So when you multiply dx on the left, the dx's cancel and you just get du. And when you multiply it on the right, I'm not going to multiply it out. I'm just going to write it down as multiplied in there. Can you all see that? So I'm going to write down 3x squared plus 1 times dx. But I'm not going to actually multiply the dx into the parentheses. Because what I want to do here is solve for dx. So how do you solve this equation for dx? Divide both sides by what? The parentheses here, right? The 3x squared plus 1. So you would get here dx is equal to du divided by 3x squared plus 1. That's what we substitute for dx. All right, let's see what happens now when we do this substitution. So we have 3x squared plus 1 over, what am I calling this? U, right. Times dx, but what's dx? I know that's du over what? 3x squared plus 1. Now look what happens there. What happens to the 3x squared plus 1s? They cancel. Yeah, and look what you end up with here. You end up with this very simple antiderivative, du over u. And we just saw that one earlier. What's the antiderivative of du over u? Natural log of u, right? So you just get here natural log of u. Actually, absolute value of u, right? So you have natural log of absolute value of u. Now you undo the substitution. What was u? What was u? X cubed plus x. So you have natural log of absolute value of x cubed plus x plus the constant. See, we get the same answer both ways, right? This way we did substitution. This way we didn't, because we were looking ahead, we didn't have to do the substitution, but we come up with the same answer. Most of the time, though, you're going to have to go through the substitution steps, okay? So you're not going to probably all the time immediately recognize, oh, yeah, I have an expression divided into its derivative, okay? Sometimes that's not so clear. So you will have to go through the substitution process, okay? So get ready for that. That's going to happen most of the time, all right? Let's try another one. Wow, okay. So here's one with trig functions. Okay, so, you know, the fact that it's got trig functions already makes it bad, but now we have to remember some of our knowledge of trig functions, right, okay? And so what you know about, well, you know a lot of stuff about trig functions, but one of the things that's really important to us is we want to recall the derivatives of the trig functions, okay, because we really need to know those. So here they are. I wrote them down into the notes. Two of these you're going to remember easily, right? Derivative of sine is cosine, and derivative of cosine is minus the sine. The other ones you probably have forgotten, but now's your time. Now's the time to remind yourself, especially especially this one and this one. These two are not as used as frequently, but derivative of tangent you have to remember for sure. That is secant squared, okay? So derivative of tangent is secant squared. And derivative of secant is secant times tangent, okay? So you really need to commit those to memory. You can write them on your survival card for the test, but it will really help if you just memorize them, all right? A little bit used less frequently is derivative of cotangent is cosecant squared, but you have to put a minus sign on it. And derivative of cosecant is cosecant cotangent. So these two rules are kind of similar, right? Except this one has a minus sign. And derivative of cotangent is kind of similar to derivative of tangent. Derivative of cotangent is cosecant squared, but you have to put a minus sign on it, all right? Okay, so this one, this one, this one, and this one, though, you really should memorize, okay? And you probably learned them in Calculus 1, so you just want to remind yourself of those. All right. Now, we're not doing differentiation, though. We're doing integration, so how are these going to help us with integration? All right, so let's look at this integration problem. Looks terrible, right? Okay, we have this quotient with these trig functions, and these are not even the trig functions that we, sine and cosine, right? The standard trig functions that we normally deal with, right? This is secant and tangent. So it looks like this is a challenging integration problem. Not at all, okay? Not a difficult integration problem. All right, so first thing to notice here is, this is a quotient. This is a quotient. I may be able to integrate this using natural log, right? I may be able to integrate this using natural log. So we're going to try to do that, and we'll do that by substitution. All right, we're going to do that by substitution. So I'm going to substitute for what? Yeah, the denominator, right. So I'm going to let u be tangent of x, okay? But remember, before I do my substitution, I have to compute du dx. What is the derivative of tangent of x? We've memorized that is what? Secant squared x, correct? Now you solve this equation for dx. So multiply both sides by dx first. Multiply both sides by dx first, and that gives you du is secant squared x times dx, and then divide both sides by secant squared x. So you get dx is du over secant squared x. Now you're ready to do your substitution, right? So we have antiderivative of secant squared x over this I'm calling u, remember, times dx, but what's dx? That's du over secant squared x, and this is always what you're dreaming for when you do substitution problems. You're hoping for some cancellation. That's the whole point of doing the substitution, is to cancel so that you end up with a simpler antiderivative than you started with. And here, lovely things have happened, right? Because the secants are going to cancel, and you're going to end up with this very easy antiderivative du over u, which we've already seen now twice, and you're going to see it hundreds of times more. Maybe not hundreds of times more, but dozens of times more. What is the antiderivative of, that's du